All right, ladies and gentlemen. So thank you for those of you who did the summative, or not the summative, the formative yesterday on covalent bonds. We will go over that, not today, but we will go over that next week. Uh, just because today what we're going to do is we are going to start ionic bonds. So we're going to go through the introduction, not really the introduction, but another introduction or reintroduction to ionic bonds. Hopefully you guys remember some of this from that video and notes you guys did last week. But a couple things I want you guys to make sure you have up and ready to go are your ionic introduction to ionic bonds worksheet and your polyatomic ion sheet. This is going to be super important in a little bit, especially that cation side, the metal side. That's going to be super important for us to have available for us. Just make sure you have both of those readily available for you. When we're looking at ionic bonds, we need to make sure we remember that ionic bonds are created when you take a metal or a cation and a non-metal and anion and you put them together. So the bond is formed. Can you guys remind me, how do you create a cation? Or what is a cation?
Is it like when you lose or gain an electron?
All right, so those are ions when you lose or gain electrons, but cations are specifically one of those two. So which one is it? Is it losing electrons or gaining?
Positive.
It's when you lose one.
Yes, when
Both
you
of
lose
those
one.
are perfectly correct answers. We're losing those valence electrons, which means we get a positive charge. So those cations are when we lose valence electrons to get a positive charge. And then what happens when we create an anion then?
Is it the opposite?
It is the opposite. So gaining valence electrons creating that negative charge. Right. So cations is when we lose valence electrons to get that positive charge. Anions are when we gain valence electrons, creating a negative charge. Why would we need both in an ionic compound? Why can't I just have all my valence electrons be lost or all of them be gained?
Because some atoms only need to lose and others need to gain.
Right. So I like that. We're going to keep adding on to that. And the fact that, especially with these electrons being gained, those electrons can't just magically appear. We're not just going to magically lose electrons. They're just going to disappear from our atom and we're going to be happy. And we're not just going to randomly just have electrons just show up for us. They have to come from somewhere else. So those electrons that one atom can lose, they're being lost, but really they're being transferred or taken by another atom who's gaining electrons. So the atom willing to lose its valence electrons will have them taken by an atom willing to gain their electrons. So those electrons don't just magically show up, but an atom that's willing to lose electrons is going to have their electrons taken by the atom willing to gain those electrons. Are there any questions on that part? All right. So then the next thing we need to remember is naming. So we'll go over all this more in detail in a little bit, but naming, just so we remember, metals will always go first. So when we're naming ionic compounds, we always go non-metal first, non-metal second. And the big thing to remember here is that nothing is going to change. Nothing is going to be added to the front of our metal's name. Will always just be the metal's name. So if I have aluminum, it will never be aluminide. It's always aluminum. It's never going to have a prefix in front of it. Sodium will never have anything change in its name. Magnesium's name will never change. The big thing, though, for these metals is we have to check if they're transition metals. Transition metals are funny because if you remember, their electrons don't go in our valence shell. They go into the shell, a different shell inside of our atom, not in the valence shell. So they go into the shell right before the valence shell. Well, transition metals are going to have random, somewhat random for their ability to lose valence electrons or lose electrons, which is why we have to have that polyatomic ion sheet. So if you look, the alkali metals, they're always going to have a +1 charge because they're only ever willing to lose one valence electron. The alkaline earth metals, that second column, only ever willing to lose 2 valence electrons. They never want more or less taken from them. Ammonium is a special circumstance where it's a couple nonmetals put together. But if we look at things like chromium, cobalt, copper, iron, lead, manganese, mercury, nickel, silver, tin, titanium, all of these, almost all of them at least, are going to be found, if we look at our periodic table, they're all found right here. They're all in this section, except for tin and lead are special circumstances right here. But all the rest of them are in our transition metal section. They're all transition metals, which means we have to read our ion sheet to see how many valence electrons they're going to be willing to lose. A lot of these elements are willing to lose multiple sets of valence electrons. So let's look at copper as an example. Copper has 2 options. We can find copper as a Cu with 1 valence electron that it's willing to lose, or copper can have 2 valence electrons that it's willing to lose, which is how it gets its 2 charges. So anytime you're looking at a transition metal, you have to check this table to make sure it doesn't show up here. If it shows up on the table, you have to identify with Roman numerals in the name for how many valence electrons or electrons it's willing to lose. So that's why it says here, we got to check for Roman numerals with our transition metals. Now, the second part of the name is going to be the nonmetal or polyatomic. Nonmetals, just like covalent bonds, you change the ending to IDE, but this time you don't add a prefix. So the nonmetal, so if we have chlorine, will become chloride. Oxygen becomes oxide, but nothing else will change with the nonmetal. Polyatomics are a little bit different though, because polyatomics, just like ammonium, is from that polyatomic ion sheet, and that's going to be our other side. So we're going to go into a little more detail with this, but that's the other side, our negative side, our anion side. So if you guys look, it's a bunch of already combined parts. So there are already 2 or more atoms or ions put together. So if we look like cyanide is carbon and nitrogen. Carbonate is carbon and oxygens. So there's a ton of them right here. You don't have to do anything with the endings. They're already in the right forms. Ate, ite, all of them are already as is. If you see one of these, so if you see ClO2, you see that, you automatically can write down chlorite as your answer, and that's it for the nonmetal or polyatomic. So you don't have to change the ending of any of these. So you never change the endings of the anions. And the cations, you're looking for those Roman numerals. I know that was a lot to take in all at once. And don't worry, we'll go through a lot more practice with this and a lot more information on this. I just want to get it all out at once. And then the last thing I do want you guys to know is when you're writing the formula, or pretty much anytime you're talking about ionic compounds, we need to make sure that we follow the rule of zero charge, which basically says that the overall compound has to have a charge of 0. So when we add up the positive side and the negative side, they should be the same number with opposite signs. So if I have a +2 on my positive side, I need to have 2 minus charges on my negative side to add up to 0. Are there any questions on any of those rules before we actually get started doing some of this stuff? All right, so let's go ahead and try this first one together. So the first thing we need to do is draw the Lewis dot structures for magnesium and for chlorine. So magnesium, how do I draw that Lewis dot structure?
You need the element symbol and the valence electrons.
And how many valence electrons does magnesium have?
2.
Perfect. All right. And now what about chlorine? How many valence electrons does chlorine have?
7.
Perfect. All right. So we have 2 on magnesium and 7 on chlorine. How many valence electrons do all elements want to have?
8.
8.
They all want 8. So chlorine wants how many more valence electrons? So it has 8.
1.
1.
It just wants 1 more. What about magnesium? It wants to lose how many valence electrons? So it has a full valence shell at the end.
2.
It wants to
2.
lose 2. So how many electrons is this magnesium going to give this chlorine?
1.
1.
It's going to give 1 valence electron away. Is this chlorine now happy? Is it stable?
Yeah.
It's stable. Is my magnesium happy and stable?
No.
No. So what are we going to do about that?
I'm gonna like throw it away.
We're going to throw it away. Can't throw away electrons. They have to go somewhere else. So if they have to go somewhere else, what do you think we're going to do with them then?
Mm,
Draw a positive charge.
Draw a positive charge. That is one way to show that things are fine, but that's not what's going to happen because we want both of them to be happy and stable when we make these ions. So let me put it in other terms. So when we are, let's say you're making coffee, okay? I don't know if you've ever made coffee before, but you get your coffee pot, you put your coffee filter, and then you put some coffee grounds in and you dilute it with water and it makes the coffee. Okay. Do you use 1 coffee ground or do you dump a lot of coffee grounds in there?
a lot.
You dump a lot of coffee grounds in there. What about water? Do you just use like 1 drop of water or do you have to use a lot of water?
A lot of water.
A lot of water. Okay, so our ions, our magnesium and our chlorine are kind of the same way, where we're not just going to have 1 atom of magnesium and 1 atom of chlorine just sitting in a container waiting to react. I'm going to take a bunch of magnesium and I'm going to take a bunch of chlorine and I'm going to throw them together and make them react. So if I have a bunch of chlorines and a bunch of magnesiums present, what do you think I can do if there's a ton of each of them already there?
You would add another chlorine.
I can just take another chlorine and this magnesium can bond with this chlorine as well. So now what's going to happen with that second valence electron on magnesium?
It's going to go to the chlorine.
It's going to go to my second chlorine. And now are all my elements stable and happy?
Yeah.
Perfect. So now that we're done showing the transfer of electrons, we need to write out this final product in ion form. So if we're writing them in ion form, I have to create an ion for magnesium. What is the ion version of magnesium? Or how many electrons has it gained or lost?
It lost 2.
It lost 2. So if I'm writing my magnesium as a charge, what charge will it have?
Positive 2.
Positive 2, because it lost 2 valence electrons, right? Right next to that magnesium with its positive 2 charge, I need to draw my chlorines, my chlorine as an ion. So I put my chlorine in brackets and I put my 8 valence electrons around it to show that it gained electrons. And how many electrons did one chlorine atom gain?
1.
It gained 1 valence electron. So what's my charge on one chlorine atom?
-1.
-1. Beautiful. Now, if we are looking at this, what did we say we had to happen for our charges? Our overall charge of this atom.
It must equal 0.
It must equal 0. Right now, as is, does my charge equal 0?
No.
No. What am I missing that would give me that boost so my charge would add up to 0?
The other chlorine.
The other chlorine. Perfect. So there were 2 of them, and they both had that -1 charge. So I need to show that there were 2 of them on my ion form by putting a 2 in front of my bracket, telling me that I had 1 magnesium because there's no number in front, and that I had 2 chlorines with a -1 charge. Now, do my charges add up to 0?
Yeah.
Yes, because I have 1 positive 2, and then I have my 2 -1s, which add up to 0. Any questions on that? All right, so then we have to do our final product for the ionic compound. When we draw it, will always be in what form? What form do we have to create it in? What form is this? What are those both shown as? What's it called when I put a charge on my atom, on my element?
Ionic?
Not ionic. We're just going to call it our ion form. Our ion form is our final product of our drawing because both of these are now ions because they have charges. So it's going to be our ion form where the overall charge must equal what number?
0.
0. Perfect. All right. We have 2 more parts for this wonderful question. And it says, what is the compound's formula? And we'll write the compound's name. So when we're finding the formula, we can look at our ion form. How many magnesiums did we need?
1,
We needed 1 magnesium. How many chlorines did we need?
2.
2. So what we're going to do is we are going to show that 1 magnesium was needed by just writing Mg. And a formula is all our atoms elements put into one line or one space. So we have Mg, and then because there's only one, we don't have to put it here. And then we have chlorine, so Cl, and because we have two of them, we need to show it by putting a subscript, MgCl2. Are there any questions on that? All right, we have one more thing we have to do. We have to name it. So when we're naming it, which element goes first, the metal or the non-metal?
Metal.
The metal goes first. And what is our metal here?
Magnesium.
Magnesium. All right, and is magnesium a transition metal?
Yes.
All right, let's check. Figure out too. Find magnesium.
It's an alkaline earth metal.
It is an alkaline earth metal. It's over here in column 2. Remember that our transition metals are in this, I want to say a pinkish color, in groups 3 through 12. Anything in here is a transition metal. If it's not in this section right here, it's not a transition metal. So magnesium is not a transition metal, so does it need Roman numerals?
No.
No, because no element that's not a transition metal needs Roman numerals. So we're done with our metal part. Our non-metal, what non-metal do we have?
Chlorine.
Chlorine, perfect. And because this was an element on the periodic table, what do we have to do with this chlorine?
Add a prefix and a suffix.
So remember, we don't have to add a prefix because this isn't covalent. But what did you say about that suffix? What does
Oh.
the suffix be?
Oh, I'd.
Perfect. We're going to get rid of that INE and we're going to change it to IDE. So our final answer should be magnesium chloride. Any questions on anything we've done so far on question 1? All right, we're gonna do one more problem together and then I'm gonna give you guys some to try on your own. So this one says copper 2 nitride. So this one already gave us the name. So what is our metal here? Which one of those is our metal?
Copper.
Copper. See you. What's our non-metal?
Nitrogen.
Nitrogen, perfect, because that IDE was an ending we added on. So if we just look at the nitro part, and we add our we look for that, it is nitrogen. So now let's figure out valence electrons. So let's talk about nitrogens first. How many valence electrons does it have?
5.
5, wonderful. What about this copper? How many valence electrons does it have?
7.
It doesn't have 7 because remember those the part that's in the transition metal part. Remember those go into an earlier energy level or earlier orbital. So that doesn't have 7, but copper is where on that periodic table? What section of the periodic table?
Transition metals.
It's a transition metal. So if it's a transition metal, we have to look where to figure out how many valence electrons it's going to have. Where to find out its charge.
The polyatomic sheet.
The polyatomic sheet. And if we look for copper with that Roman numeral 2, what would the charge on that be then?
A +2.
A +2. So this Roman numeral 2 tells us that there's a +2 charge, or that there are 2 valence electrons on this copper. So now let's draw out our copper. Let's draw out this compound, this ionic compound. So what's going to happen with my 2 valence electrons on my copper?
They're gonna go with nitrogen.
They're going to get transferred to nitrogen. Is my copper stable and happy now?
Yes.
Is my nitrogen stable and happy?
No.
No.
So what do I have to do?
Would you add another copper?
Add another copper. Perfect. So I'm going to add a second copper. And now what's going to happen with now?
One electron would get shared with the nitrogen.
Perfect. Nitrogen's taking that 1 electron. And now is my nitrogen stable and happy?
Yes.
Are all my coppers stable and happy?
No.
All right. So what am I doing now?
Add another nitrogen.
Add another nitrogen. Perfect. All right. What's going to happen now?
The one electron would get transferred to nitrogen.
Perfect. Is everything stable and happy?
No.
All right. So what am I going to do now?
Add 1 more copper.
Add another copper. What's going to happen now?
The 2 valence electrons will get into nitrogen
Transferred.
or transferred.
We're transferring them into nitrogen. Is everything stable and happy now?
Yes.
Yes.
Whew. Man, that took a while. Lots and lots of transfers of electrons. So now let's write our compound in ion form. So who can tell me how to write this in ion form? All right, let me ask this. What is my charge on copper?
A +2.
A +2. So we're going to write copper as a +2. And then we're going to write down how many coppers we had. How many did we have here?
3.
We had 3, so that 3 goes in front. Now we have to draw our Lewis dot structure for our nitrogen ion, which means we draw all 8 valence electrons on it. If nitrogen has 8 valence electrons, what is the charge on a nitrogen atom?
-3.
-3. And how many nitrogen ions do we have?
2.
We have 2, so we're going to put a 2 in front. Let's just double check to see if our charges add up to 0. So we have 3 times that +2 plus the 2 -3s. What does that add up to?
0.
0. So we did it correctly. And last but not least, let's come up with our formula here. So what would my formula be for this compound? Remember, we write our element symbols, and then the subscript tells me how many we have, getting rid of those positives and negative charges. So what would my formula be?
Would it be Cu3 and then N2?
Perfect. And then we're done. there any questions? All right, I think there were 7 for you guys to try, if I remember correctly. 8. There are 8 practice problems for you to try. So if you guys want to stay in case you have questions, wonderful. Otherwise, have a wonderful rest